Okay, so it's the second and last day of celebration of two things, which is the Hamilton's 220th anniversary and the Hamilton Mathematics Institute 20 years. Today, this morning, is special for several reasons. One reason is Erik Verlinde, professor from University of Amsterdam, is the only speaker on this conference who is also affiliated with Hamilton Mathematics Institute. He is Simon's visiting professor for now 2 years. This is one. Second, we had to put this talk at 10 o'clock because at 11:15, there will be celebration of Indian festival called Diwali, and it will be very noisy on the front square. So what will happen is that Erik will finish the talk, they will start dancing, and then we come back at 2 o'clock. At 2 o'clock, there will be talk by Gregory Gabadadze from New York University and Simon's Foundation. So that's a special thing. There is a third special thing during the last talk, which will be given by Roselyne Bell-Barnell, but we will talk about that later. I want to introduce Erik today as, in my view, outstanding theoretical physicist in tradition of Hamilton, in a sense, that contributed to mathematics, contributed to theoretical physics, and his contribution in mathematics, once we realized when we were younger, when there was a talk by mathematicians at the Institute, we could not understand the way a famous mathematician was explaining Erik's results, which is a Verlinde algebra. And then Verlinde algebra, I understand, was in the start of topological quantum computing, much before of everything. So Erik, already being a student, made this outstanding contribution, which is both in theoretical physics and mathematics, as I said, like Hamilton. And then he went and did many, many things, but now it is a stage when he's back to black holes. So Erik will be talking about, title is here, please.
Thank you very much, Samson. Well, it's a pleasure to be here. Indeed, I enjoy always my visits here, and this is a wonderful institute. And this special occasion of the 20th anniversary for the Hamilton Institute, and of course to celebrate Hamilton. When I was asked to give a talk, I gave a general title because this is the general field I work in, so I still had to decide what to talk about, and there are three topics that are interconnected. Let me make clear, first of all, I enjoy mathematics, but I feel myself mostly a physicist, which also means that I formulate my questions generally about trying to understand how nature works. And so the connection between these topics is also telling me something about a deeper understanding of gravity, and also about many things that we want to know about the combination of quantum mechanics and space-time. So I will talk about various things. Here's an outline. I will indeed have a brief introduction of black holes, strings, and entropy, why I'm connecting those. But then I will discuss three topics that are closely connected to the work of Hamilton. In particular, I will start, the first part will be sort of general, but the second part will be quite specific about a way of thinking about Hamiltonian dynamics in an emergent kind of way, where it sort of appears from what's called an adiabatic reaction force. I will then move on and sort of apply this in context of black holes and some recent developments where also the Hamiltonian, sort of related to, of course, the work of Hamilton, will appear, but again in a context where it kind of emerges from an underlying description. And string theory indeed is the way sort of to understand these microscopic pictures. But I will start by telling you first something about black holes, where there's an important clue about how we think about space-time and how it's connected to quantum mechanics. So the starting point is the famous formula of Bekenstein and Hawking for the entropy of a black hole. So black holes are these mysterious objects which have an horizon, and what Bekenstein and Hawking figured out is that the entropy of a black hole is proportional to the area of that horizon. And Hawking famously also discovered that there is a temperature associated to black holes, which eventually led to reformulations of the equations for black holes as the laws of thermodynamics. This, I think, is a very important breakthrough and also important hint about how we should think about the gravitational equations. But there has been a lot of discussion in the recent decades, actually, ever since the discovery of Hawking, about what this actually means and what we can learn from thinking about black holes and interpretations of this formula. And string theory made important contributions there because it actually was able to show that this entropy is not just an analogy with, well, thermodynamics. There's really a microscopic theory that might explain exactly what the microscopic states are of black holes. So we believe this entropy really counts something of black holes. Another interpretation of the same formula is related to entanglement entropy, which is kind of a slightly different quantity. And it turns out that the same formula also describes the entanglement even in vacuum space-time. And this is an insight that came from studies in string theory, and where we indeed think that understanding this formula means also we're going to understand more about space and time itself. So, indeed, the entanglement entropy on the picture here on the left, you can think about it as sort of that this horizon, this is a space-time picture, separates two worlds that are, well, glued together at the horizon, and the entanglement entropy would then be describing the entanglement between these two sides, because the state, the vacuum state near the horizon is just like the vacuum state in our world, and there is entanglement, as we will explain in more detail as we go along. Another important property of black holes is that because they have such a high entropy, this entropy formula is enormously large, we also know that if we think about them quantum mechanically, and count how many states there are, it's an enormous amount. And that also means that the energy levels, if you think about it like an atom or something like that, is enormously dense. And so that means also that the system that describes black holes presumably has a chaotic description, because the spectrum looks like kind of this, where you really cannot almost distinguish between different states, which also means that transitions between these states will take an enormous time, but there's also a lot of chaotic dynamics. So it's not an integrable system of any kind. Now, what makes the connection with gravity sort of interesting is what I mentioned, namely that the laws of gravity can be recast in the case of black holes as the laws of thermodynamics. And the simple fact that the area of the black hole increases, which is sort of why if you throw in a mass, well, we think about this as sort of due to the gravitational equations, but when you interpret this in terms of the entropy, you get precisely the first law of thermodynamics, which is a law that we know we can derive from sort of a microscopic picture. And so, well, what does that mean? Does that mean that we can also derive the gravitational equations from a more microscopic picture, thinking about space-time as sort of being derived from this underlying microscopic theory? That sounds like a lot of words, but it's exactly what string theory has been able to do, is to show in certain cases that this program can be completed. There is a formulation of string theory that eventually led to a theory which is now called ADS-CFT, where indeed we can show there is a microscopic theory which obeys, well, microscopic laws where there's no gravitation inside of it. The theory lives on the boundary, but then in the bulk we have a gravitational theory that emerges where even the space-time in the other direction, so there's an additional dimension that's being grown here. We call this well, in this case, the most famous case, we have some 4-dimensional space on the boundary and a 5-dimensional case in space in the bulk. But there are other examples, but there's always an extra dimension where the gravity is living. And this is an example of what I would call an emergent theory of gravity, where the microscopic description is that of the conformal field theory. So what is the connection now between strings, black holes, and entropy? It's indeed that string theory can explain the microscopic entropy of black holes, and that black holes teach us something about really the nature of space-time. And I think this is going to be the conclusion. I'm going to write it down. It's quite a strong statement, but what I will explain in the rest of the lecture will sort of be elements of what's going on here. So what I'm writing here is that the study of quantum black holes and string theory really points to what's going to be a microscopic quantum statistical theory of space-time, where quantum entanglement plays a crucial role. And it's really an emergent description. So I will, well, this is sort of what I'm claiming then, that indeed there is some new theory appearing which sort of combines elements of string theory and the insights of black holes, which is kind of the statistical physics of quantum space-time. So this was my introduction and into the topic. So now I'm going to go and discuss how Hamilton's work sort of comes into this, this whole set of ideas. So when I was preparing the talk, I thought that I would only talk about Hamilton's famous Hamilton equations. But there's actually also a nice way that even his quaternions come into the game. Because there's, well, a funny way in which quaternions, I mean, you might say that the Hamilton, because of the Hamiltonian, was kind of, the Hamilton equations was kind of related to quantum mechanics, but even the quaternions have sort of a quantum nature to them. And indeed, if you now look at models that we are making, say, for black holes, they kind of are secretly there. There's the Dirac operator, but I want to make a slightly different point here, namely, you can think about quaternions. First of all, I'm writing down explicitly here as numbers that don't commute, so that's already suggesting some quantum nature of it. But the other way to interpret them is as a way of writing, well, qubits even in this language, because these operators are very similar to the Pauli matrices or the operations that we do on qubits. And this can be made quite explicit. If I write down a qubit is a two-level state, where generally we write it down in terms of complex numbers, but you can also write it down as a state in a quaternionic basis. And if you put the norm of the quaternion equal to 1, somehow this will, well, become equivalent actually to a qubit. And you can even write all the elementary gates that we put on a qubit in terms of the I, J, and K operators. Normally we call them X, Y, and Z, sort of like the Pauli matrices, but they are in one-to-one correspondence with the quaternions. Now, this will indeed sort of come back when I'm going to describe models of black holes. And one way this, well, needs to be viewed then is we want to ask, well, if this is one qubit, so how do I describe more qubits? If there are n qubits, well, the quaternionic field cannot do this by itself. You have to do some extension of this. And in particular, also this notion of entanglement, is there some way we can bring this in? I will come back to that in the end of this lecture. So I'll now start with indeed discussing Hamilton's work on Hamiltonian dynamics and see how it connects to these questions about, well, black holes and entropy. So I will view Hamilton's equations. First of all, I think they're elegant. They're in certain situations even powerful, and in particular in statistical physics, for instance. And they're very universal. I mean, any system can be usually put in this form. But is the Hamiltonian dynamics really fundamental? Is it really how the world works at the microscopic level? One thing that I like to say here, these are classical equations, and our world indeed has positions and momenta, but you may wonder whether that's really the language in which the microscopic world is formulated. Of course, these variables are quite formal. I mean, we can have other systems where we have conjugate variables, but it's not always clear whether the system we're looking at is really the microscopic one. So what I'm going to discuss is a emergent kind of Hamiltonian dynamics. So first of all, let me rewrite the Hamilton's equations in a slightly different form. Can I do pointers with this or no? Anyway, so the equation I write there at the top is again Hamilton's equation with more momenta and so on, but I can combine the p's and the q in one set of variables, which I call phi, And then I can introduce this symplectic form that Maxime also talked about yesterday. And what then can be done is actually you can write the Hamilton equations in this sort of suggestive form, because what is written there is the variation of the Hamiltonian with respect to, well, all the phase-space coordinates. And on the left-hand side, you have some quantity that involves the time derivative, but also the variation of the field. And the reason I think it's suggestive is because there's some way in which the first law that I showed you also has some variation of an energy in it. So indeed, as I will show later, this equation in particular situations indeed becomes the first law of thermodynamics. I'm going to make it slightly more abstract even by using form notation. So I think about a phase space more generally, where I have a 2 form, where I write it as the d of a 1 form. And then the geometric action, as I call it, is simply the integral of that 1 form. So there's no Hamiltonian, and in that sense there's no dynamics yet. But if I choose a function on this space, and I call it monotonic by thinking about it, that I can have a foliation of the phase space where I pick certain values of this function, which I then put constant, then suddenly there's sort of a dynamics generated, because I can go to a smaller phase space by what's called a symplectic reduction. You solve for, well, this function being constant, and then you mod out by the dynamics generated by this function. So let me show this a little more explicitly. So without much loss of generality, I can write my symplectic form in this, well, PQ basis, but I added one set of variables, namely energy and time. So this is just in the beginning to write down an action that indeed does not involve a Hamiltonian. So the energy now is written on the place where we normally write the Hamiltonian. Now this function S also indeed generates a flow, and it can be made constant, and the flow is simply calculated from the Poisson brackets and so on, and so you get a flow on this set of variables. And only if we choose this function S in one particular form, we recover Hamilton's equations. I can write this function S, namely as that I identify the energy with the Hamiltonian, and then I can eliminate the energy and the time. And you see in the last equation even that, or the one with last equation, that the time and the variable S, which is sort of a formal time direction, sort of become identified. But this is a way of rewriting Hamiltonian dynamics, but as a constrained system on a larger phase space. The reason I mention this is there could be other ways in which the system likes to have a constant quantity on there. So this function S may not really be of the form that I write down. It might be some other function. Yes, okay. But now I'm going to think about it in a slightly different way. Namely, what I'm going to do is actually start from a system where there's no Hamiltonian and not even a symplectic form. I'm going to think about a set of variables, phi, which I still call phi I, but there's no phase space interpretation yet, but they're simply variables that couple to a other system, another quantum mechanical, well, in this case, a quantum mechanical system, where the Hamiltonian somehow depends parametrically on these variables phi. And then I can study how a particular eigenstate of this Hamiltonian behaves as a function of phi. And I do this adiabatically. So this is an adiabatic system where the phi variables are thought about as really slow variables, so that the state of the quantum system stays in one particular eigenstate of the Hamiltonian. In that situation, you can define what's called the Berry phase. Namely, you can look at how the state varies when I vary these parameters phi. This phase is a connection on the space of phi, and actually can be used now to define a symplectic form. So one way to write a symplectic form is Well, here I abbreviated actually the same equation by introducing again this variation delta phi. Then I can get my symplectic form by taking another variation, and this is what's called the Berry curvature. And so there is a way that when you couple some system of slow variables, which I think about these as these phase space variables phi, to a underlying microscopic system, that you induce a curvature, which then becomes kind of the symplectic form on my manifold. These kind of systems are quite common in nature. One way we know them actually from textbooks is the way that Born and Oppenheimer solved the way that helium, for instance, is formed out of binding to protons and to electrons. And one way this is done is by separating the system in what is called slow and fast variables. This is, by the way, a notion you can even introduce in classical system. If you have a system that really reacts fast to some other system that's driving it, then there's a back reaction, and you can calculate that by what's called an adiabatic assumption. And generally, the assumption indeed is that you keep the energy or the eigenstates of your Hamiltonian fixed. And this creates an adiabatic invariant, namely the phase space volume that is sort of involved in these, below a certain energy level, for instance. This has been studied in great detail by, among others, Michael Berry, also who, of course, is famous for discovering the Berry phase. And he has shown analogies between what happens in classical mechanics and in these quantum mechanical systems, and indeed calculated what are called adiabatic reaction forces that are driven by entropy. So this is kind of a way in which an emergence Hamiltonian dynamics can appear. So in words again, so I have a microscopic, what I call fast, kind of quantum system. It need not be integrable, and generally can even be chaotic, which means that there's no closed orbits in the classical theory, but also that means that in the quantum theory, the energy spectrum has this very dense behavior, and it also means that you indeed has an adiabatic invariant must use the full entropy of the system. Now, if you then change your slow variables, which are the macroscopic variables that, say, our world sort of is aware of, there can be two responses, twofold response, namely I create this Berry curvature that will induce this symplectic form, and I write down this action integral as identify this as the Berry phase. But if you also take into account this invariant, sort of the adiabatic invariant of the theory, you will actually also induce a Hamiltonian dynamics. So Hamiltonian dynamics can be induced by this underlying system. I claim that this is actually the way that dynamics is being generated in space-time. Indeed, in what I'm going to explain next is near black hole horizons, but even in horizons in our space, you may wonder what is really driving the system. What is the dynamics coming from? It turns out that even in this situation, we should think about the microscopic underlying degrees of freedom as inducing the Hamiltonians that we have in our space-time. So normally we think about the Hamiltonian as sort of time going up, sort of in a normal time direction, but when we have a horizon, the asymptotic time at infinity actually becomes more like a boost operator, because if you are indeed near, say, a black hole, in order to sort of not fall in, you need to accelerate, and so you kind of create what's called a Rindler horizon, where there are indeed some light rays that will not be able to reach you. So you can see that there is really a black hole there, because light cannot come from inside towards you. But then near the black hole, that means you have to accelerate. And so the same Hamiltonian that at infinity sort of generates time flow near the horizon becomes then a boost generator. And often in that context, when we study it near horizons, we give it a different name, because normally we think about Hamiltonian flow as going up. So usually then it's called K, because that's sort of what a boost generator looks like. It often has a name also because what we will show is that this generator can indeed be induced from entanglement. It's called a modular Hamiltonian. And it's going to be indeed the last topic I'm going to be describing in this lecture. But first let me go back to Hamilton's formalism and the way it's sort of connected to describing what's going on near this horizon. What I'm going to describe is called the covariant phase space, and it's a formalism that was introduced by Wald. One of the nice things about his formalism is that we don't have to assume that we have a given Lagrangian for the, how should I say, it need not be Einstein-Hilbert action for gravity. Any Lagrangian for the gravitational theory will allow me to derive what is called a first law of thermodynamics for black holes. This is important because in string theory we know that the Einstein action is sort of a first term in an expansion where there might be higher order corrections in what's called the string scale. And so you want to know whether this whole idea of Bekenstein and Hawking, that there's an entropy associated to horizons, is still correct. And can we still derive this first law of thermodynamics, of black hole thermodynamics? So this turns out to be possible by basically following the same steps that everyone follows to derive Hamilton's equations. So I'm going to actually show indeed that Hamilton's equations sort of imply the first law of black hole thermodynamics. So the way that happens is by first starting from a Lagrangian, an action that is covariant, but then we quickly want to turn it into a Hamilton formalism by, first of all, using the equations of motion, or sort of the variation of the Lagrangian, to derive the symplectic potential. So this potential theta that gave me the symplectic form can be seen or actually obtained from the action or the Lagrangian by doing the derivation of the Euler-Lagrange equations. As you know, you have to then often do a partial integration, which means you're dropping a boundary term. And that boundary term actually contains what's called the symplectic potential. So the equation that's written down here, so the E stands for the Euler-Lagrange equations, and this theta then is the symplectic potential. Now, in order to find the Hamiltonian, you do what you normally do well, if conserved quantities, you apply Noether's theorem. And so there's a Noether charge that if you integrate it, it would give you the Hamiltonian. So the Noether charge looks exactly like the normal expression we have for the Hamiltonian density. And then you can write down the Hamilton equations in the same form as I had them earlier. Namely, I can look at the variation of the Hamiltonian, and then on the left-hand side, I use the symplectic form, indeed with a variation and a time derivative. So this symplectic form is obtained from the term in the Lagrangian, which is called theta. There's a slight change in the earlier notation, and that's because here I'm integrating over a space, so the fields, the phi's that I have here are basically fields on space-time. And the integration region is what's called the Cauchy slice, so it's say t equals 0 slice. Because that's the way we formulate Hamiltonian dynamics, by taking time slicing. Now there is something very special happening in a general covariant theory, because it's invariant under coordinate transformation. So even the time translations that I'm going to use to derive the Noether current is actually a coordinate transformation. And that implies that the Noether current is not something that you can write down sort of trivially. Noether charge generally of current is conserved, and in this language it means it's a form that is closed. But due to the general covariance, what it actually tells you is that this expression must be a total derivative. because then it's trivially closed. I mean, it's an exact form. So this is what general covariance tells you, is that this current J that I wrote down is the D of some object which we call Q. And this has the implication that the Hamiltonian now is not a thing that we integrate over space, it becomes a boundary term. That's a very famous result in general relativity, is that energy is measured from the boundary, like sort of a Gauss law, and therefore the expression for the energy can be written as a term at infinity. Well, that's if there's no horizon, because if you have a horizon, I can choose the surface C that I'm integrating over to start from infinity and end at the horizon. That's a very natural thing to do. Actually, I don't have full time to explain it, but if you go to Euclidean space, actually the space basically ends at the horizon of the Euclidean space-time. So there is a way to consider only the region outside of the horizon. And so when I think about this Hamiltonian as being associated only with the exterior of this black hole, then there's actually two boundaries to my Cauchy slice, namely one at infinity and one at the horizon. So when I'm going to derive now the Hamilton equations, I want to vary this Hamiltonian, and now I get two terms, namely one at infinity and one at the horizon. And so the Hamilton equation I'm repeating here again. I already wrote it down earlier. But now what I claimed is indeed this Hamilton equation actually gives me the first law of black hole thermodynamics. Why? Because the first law of black hole thermodynamics is derived in a geometric background that is time independent. So we basically look at the black hole and then we vary it a little bit, but the solution in space doesn't depend on time. So the left-hand side of this Hamilton equation actually vanishes, which means that the right-hand side actually, which were two terms, need to be equal. And if you work out what these two terms are, well, one of them is the energy, indeed, the energy as we measure them at infinity. It's called the ADM mass. If you vary it, you should get the same result if you vary the other term, which is then the entropy. And so you indeed recover the first law of black hole thermodynamics basically by the same methods by which we use to derive Hamilton equation. So that's a direct way in which Hamilton's formalism applies and can be applied in this context of black hole thermodynamics. And again, this is a derivation that doesn't use anything about the Lagrangian. I haven't told you what the action looks like. If you would put in the Einstein-Hilbert action, this will become the Bekenstein-Hawking formula. So this is then a generalization, and it's called often the Wald entropy, because it was Bob Wald who thought of this derivation, indeed using the formalism of Hamiltonian dynamics. This, by the way, can be also done in a very concrete example where we do know also what the microscopic description is. Because I'm telling you this is an entropy, and now you may ask, is it really a microscopic entropy or an entangled entropy? Well, it turns out that if you do this even in flat, or so I should say not flat, but empty space, you can do this in ADS, in empty de Sitter space. So here there's no black hole, and here I'm looking at a observer that's indeed accelerating along this red line, and by that it creates this Windler horizon. So the picture I've drawn here also indicates the Cauchy slice that goes from the boundary, which is sort of what I called infinity, to the horizon. The horizon is indicated with the letter H, and the boundary at infinity, well, in this notation actually, it was actually used for another talk anyway, I denoted by SR. It's some region on the boundary, but there's also a Cauchy slice, which now is called sigma. So the energy that we defined, the Hamiltonian, was the integral of the Noether charge, but Noether current, I should say, but then the quantity that's J is a derivative of some Q. Therefore, we have again these boundary terms, one at horizon and one at infinity. And you can do the same steps as I did for the first law of thermodynamics of black holes. But now I apply this in empty space. So there's no black hole in this picture. And so this is only measuring the entanglement that's in the vacuum. Now, it's a very famous result that in ADS-CFT there is entanglement entropy in the vacuum. It's called the Ryutaka-Miyagi formula. So this method can be used to derive that formula. And indeed, if you assume, again, that the bulk gravity is described by Einstein's theory, you get the area law. But you can also go the other way. If I assume indeed that the entanglement is given by the area, where I then introduce some constant that I call G Newton, but has nothing to do with gravity, you can actually go the other way around. Because what I'm deriving here is a microscopic equation, which is called the first law. But it turns out that its macroscopic interpretation becomes the Einstein equation. So this idea has been used concretely by various authors in the anti-de Sitter context to derive from the microscopic boundary theory, the CFT, you can then derive the bulk equations. And indeed, also in this context, the symplectic form in the bulk is given by a Berry curvature of the boundary theory. So when you think about the boundary fields, sort of the correspondence, actually there's some correspondence between the boundary values of the fields and the probing the microscopic theory. And then you can do exactly this step that I explained about the Berry phase and Berry curvature. And yes, you do get the bulk symplectic form. So what I described about this emergent Hamiltonian dynamics is entirely realized in this story. And now you can even ask, well, what is then the role of quantum entanglement? So this S indeed is an entanglement entropy. And this can be made very explicit also, because if you just follow Hawking's original derivation, or what has been recently more done by well, in particular, Juan Maldacena, who indeed wrote down a microscopic state that describes a black hole that's connecting two sides across the horizon. In this case, it's an eternal black hole, so then an eternal black hole actually has a wormhole that connects sort of of Einstein-Rosen bridge, it's called, that connects the two sides of the black hole. And so you also need actually two CFTs, and we call this the left and the right one. And then the state, which looks like the vacuum well, near the horizon, is an entangled state, which entangles the two CFTs. And the operator that I wrote there, I didn't call it the Hamiltonian, because it's indeed the boost generator near the horizon. So if you take this state, calculate its density matrix, you find a thermal state where the thermal temperature, or even the Hamiltonian that we normally write down in the thermal density matrix, is given by this K. So this operator is called the modular Hamiltonian, again, a way in which Hamilton's work sort of comes back. This is kind of a formal thing because it can be defined for any state. You give me a state that I call psi. I think about it as describing a part of a space where there's also another part of the space. And so even in mathematics, people have done this in operator algebra theory, where they think about then the state on only part of the space and define a sort of effective Hamiltonian that describes a flow on that space that is generated by the entanglement. Maybe in the following way, I trace out the other side, I obtain a density matrix. If I would use that density matrix to define entropy, that would be the entanglement entropy. But I can also write it in the form of a thermal state, and then the Hamiltonian, where we normally write the Hamiltonian, is exactly where K then is written. So it defines a flow called modular flow, and you might say this is sort of an emergent time. And in particular, Alain Connes, a famous mathematician, actually uses this a lot actually in his work, and indeed talks about this as an inherent time that you have in terms of Well, if I just start very abstractly just from the operator algebras. So the other thing that we can do with this model Hamiltonian is derive a first law of entanglement. Just from the equations that I wrote down there, you can write down a variation of the entanglement entropy and compute it and express it in terms of this model Hamiltonian. This is just, well, simple steps from the equations. So this is a microscopic derivation of the first law. And this equation is the same equation that then was derived from the gravitational equations. So we somehow have a correspondence between the microscopic theory and the gravitational equations. I may finish a little early, but anyway, I will have two more things to say. One thing is that indeed the recent developments are more about really discussing what's going on near the horizon and to think about how space-time comes about. Because in this model of, well, the model we know best, ADS-CFT, we know very well what's happening at the boundary, but when we really want to go into the bulk from the microscopic perspective, we have not so much control. So one of the things that people need to do is take a large n limit, and then people know quite well what kind of operators I have to write down on the boundary theory in the CFT to describe bulk fields. But to really show that these operators satisfy the algebra that we know about bulk fields, we have to go through some limits. And this is where, indeed, this language of operator algebras, in particular for Neumann algebras, have become very useful. And these concepts about model Hamiltonians also appear in that context. And recently, there's a lot of excitement due to work by Liu and Leuthauser, who show that there's not just a boost Hamiltonian, because this Hamiltonian is really doing a boost in that direction. You can even have other sort of generators near the horizon that describe translations. So there are, in the local neighborhood of the horizon, generally you like to have some Minkowski space, so you expect there should be some Poincare symmetry where boost is only one of the generators. And you also need, namely, translation operators that sort of translate in time or translate in space. Turns out that just very abstractly, without assuming anything about the existence of a space-time, if I can show in certain type of algebras, these are called type 3 algebras, if there are inclusions of algebras, and you should think about this sort of as having a region of space that's contained in a larger wedge of the space, in such a way that if you apply now this time flow, that the algebra sort of keeps, well, being contained in itself. That's called a half-sided model inclusion. And then you can prove that there is an operator in the theory that does a translation in that direction. And you can do this for the inclusions that go to the future, and you can do it to the past, and then you get two generators locally sort of that look like translations along the directions of the horizon. And so you're building up a space-time picture, because once you have these operators, you can really move points, and you see that there is a space-time emerging just from pure abstract algebras in quantum theory. So I think about this sort of as the algebra of the microscopic theory, and that then we have to sort of see how the space-time then comes from that. And the central well, mechanism by which this works is the entanglement entropy. But there's also what's called the chaotic dynamics. And this kind of can be seen already from the algebra of these operators. So if K is the boost generator, P are then translations in the plus and the minus direction, then they satisfy an algebra with the boost generator. That's sort of the normal Poincare algebra. Then you can, of course, solve this equation, and boost, they work by multiplying, say, the x plus coordinate up by e to the t and shrinking the minus coordinate with e to the minus t. This, in Hamiltonian dynamics, is called Lyapunov behavior. So there is actually a chaotic system, because Lyapunov behavior is generally what happens, well, because of some butterfly effect that we associate with chaos. Turns out that these exponents is even the maximal exponent that's allowed in any system. So the microscopic system is not just chaotic, it's maximally chaotic. And then we can explain these emergent sort of Poincare symmetries. So this is why people are now thinking about horizons as chaotic systems. It's a particular Kitaev who has been thinking a lot about, well, how these things can emerge, and he has even toy models in 2 dimensions where he can have black hole horizons emerging from a chaotic system. And this is where I want to indeed go back to how I construct toy models for chaos. And this is connecting now to what I said in the beginning, because what we're going to do is make a model that's sort of the most basic model where we can have some entangled qubits, even smaller than qubits. So what Kitaev worked on is a model that was first written down by Sachdev and Ye, and so now it's called the Sachdev-Ye-Kitaev model, or SYK. And the idea is that here we're looking not just at 1 qubit, but actually at n qubits. But the way to get n qubit is to write down what's called 2n Majorana fermions. And then you want to entangle them, and this you do by allowing them to interact. Now, if I would have only 2 Majorana fermions, their algebra is written down there. Majorana fermions are operators that square to 1, and they anti-commute. But 2 of them precisely describe 1 qubit, and so there must be a map to quaternions. And you can indeed write down explicitly what they are. And so there's 3 operators, namely psi1, psi2, and their product. To be honest, on the way here, when I was walking in here, I actually realized I had a sign mistake in here, but anyway, you can figure it out. The last one should have a minus sign, I think. But anyway, it works out. If you multiply this using those rules, you get exactly Hamilton's quaternions. But of course, the model that we've built has many more qubits, so there's some extension of this idea of Hamilton that even goes towards the, well, quantum chaotic descriptions of black holes. So here I want to actually end, and actually I put down my sort of slide about the connection between these topics I talked about, where I think the conclusion, I hope, sort of now becomes a little more understandable, that I think the study of what we learned from string theory and black holes is really pointing to a microscopic theory of what I call the emergence of space-time. And I think this involves quantum entanglement, chaotic behavior, even things like scrambling, or I haven't even talked about what's called quantum error correction, but there's a lot of development going on in this field, not just by myself, but many people in the world are working on this. And it looks to me like we're really starting to understand what quantum space-time is. Thanks also to the work of Hamilton.
Thank you very much. I think that what you told us is in very much of the style of Hamilton, looking into the heart of the problem. And I believe what you are talking about is the most forefront of what we've been thinking in theoretical physics. And theoretical physicists are distinguished in the sense that they are probably one of the best to identify the main part of the problem and then build out of it. My only comment would be here is that Hamilton could not believe. It's not working? Yeah, Hamilton would not believe that this can go this far, you know, what he was doing. It's amazing. Before I open for the questions, I forgot yesterday certain duty I had to perform, and I will do it now, and then we take questions. So 20 years ago, we asked government to make coins dedicated to Hamilton's 200 years, and I have a central bank and financial services authority of Ireland making coins, which has on a face nabla operator of IJK Hamilton, and it's dedicated to Hamilton's 200 years anniversary, and I want to give you as a present.
Thanks a lot. Very nice. very happy.
Unfortunately, I gave the yesterday's speakers, I gave this privately. I forgot in my office the coins. But today I will be doing in proper way. Now we take questions. Yes, please.
Thank you very much. I missed why you call the Hamiltonian modular. Could you explain that again?
Well, it comes from a theory of Tomita and Takesaki. And so they have some operators that eventually, my understanding at least is that it's a polar decomposition they're doing where there is an angle coordinate and a norm. So it's like the modulus of the operator. I think that's kind of where it came from, but it's now being used so much that most people don't even, well, think about where it comes from. I don't think it has anything to do with modular group as we know it, so say for Eisenstein series or things like that. I mean, there's a different meaning of the word modular, which I think is related to modulus of a certain operator, something like that.
Well, first of all, thank you very much for a very interesting presentation. My question comes from someone who is involved in understanding black holes from astronomical observations, be it in gravitational waves or being in imaging of supermassive black holes. What are the signatures that this, entanglement entropy or quantum chaos would leave on the observables in terms of gravitational waves or
Well, that's a very good question where I don't think we have a answer yet. Some people have made models. What I didn't talk about here is really the puzzle that came out of Hawking's calculation, what's called the information paradox. If we think about the information paradox, we start realizing that it can only be solved if we assume that the horizon is a very special place. Certain strange things must happen. People even started questioning the interior. Sorry, I need some water, sorry. People even started questioning the existence of the interior. That was called the firewall paradox or something like that. So that was an indication that something really special may happen. And if it's true that this firewall is slightly outside of the horizon, or other models were called fuzzballs, of course then there might be signatures. So people looked at these echoes and so on. I don't think this is actually what's happening here. I think this chaotic picture is probably more correct. But the question is what is the distance scale over which this happens, and whether the gravitational waves really probe that region. Because as far as I understand it, it's very difficult to get signals from very close to the horizon. It can only happen if their incoming waves sort of get reflected back or something. So I don't have a theory there that tells me, will tell you what to really look for. But it's certainly not excluded that what we now think is the description in general relativity will have corrections because of the microscopic description that we are having here. And personally, I'm not interested only in black holes. Actually, I'm mostly interested in other regions of space-time, for instance in cosmology, because I think these ideas about the emergence of this space-time will be very hard to test in black hole context. I think it's probably, well, many similar arguments are holding for, say, cosmological horizons, and I have more hope that this description will teach us something about early cosmology, or maybe even things that we now don't know about dark energy or other parts of the universe.
Thank you for the great talk. I've got two questions. So in the beginning of the talk, you said that black holes have lots of microstates, and therefore they should be chaotic. But that argument I haven't quite understood, because, well, they might be integrable with huge multiplicities. So that would be my first question. But then it's a bit related to what you said in the end of the talk. You said that in order for the space-time, in order for the translations to emerge, the black holes, so in general, gravity has to be chaotic. And my second question is, if black holes were integrable after all, then what? There would be no space-time, or like just maybe you can comment.
Yeah, the existence of these translation operators is really what is required to have a smooth space-time. And the fact that you get locally this Poincare algebra basically tells you have to have a chaotic system. And the way I understand it is that the entanglement is even required to have the space-time connected. So what's actually happening when information gets transferred to the other side of the horizon is that it first gets scrambled over all degrees of freedom. Then there is some transition happening and you have to be reconstructed on the other side. And it's impossible to do it if you're not scrambled. And this firewall paradox actually goes about this, that there's a very particular way that the space-time does this. And if you have the wrong vacuum state, you will not be able to get to the other side. So entanglement by itself is not the full story. It's also this chaotic dynamics and a lot of, well, so I think this idea that black holes are the fastest scramblers, they are the most chaotic systems we have, I think it's going to be important in understanding just generic how we think about emergence of space-time. And so an integrable system would not have sufficient ways of making transitions between various states. The information would not get scrambled, and that would be really a problem in describing the local structure of the space-time.
Okay. Actually, I have one comment. This gets so nicely works where you present it in the beginning and the end in general relativity, because Einstein's general relativity is a constrained system. Everything is constrained. So it's like a system where everything is a Gauss's law. And because of that, I think it's unique and it works where you described. Basically, in proper way, only boundary contribution comes. There is no Hamiltonian. Mm-hmm. The equations of motion are basically constraints. I think that
is valid if you quantize gravity, that's correct.
Right, that's how Dirac explained in his lectures, yes. Okay.
But I forgot even to mention that the action that you wrote down with Anton is actually also one of these actions, because
right.
Because it's kind of coming from a Berry curvature as well, right. So you can actually analyze that and see how that action comes about. Or the Schwarzschild theory in SYK also comes from the same kind of...
Right. The reason for that, by the way, was that we were interested in cocycles. And cocycle for the group in group homology can be written in a form that you had written. Remember, you had omega ij, delta phi dot, that's the way. And then it goes and goes. But anyway, that's just a comment. Was this completely constrained system is unique, and this should be important in this conversation. Now, before I thank Erik again, I just was standing here and we're looking, and our university was very interesting. That gentleman, William Molyneux, was the first mathematician in the university. See, it's the middle of 16th century. And the next one is Jonathan Swift, which was probably most famous writer here, right? So that's how university was. The first two guys are a mathematician and a writer, and I hope that this tradition will remain. On the other side is a queen and the bishop, but here we have mathematician writers. This was how the university was, okay? Thank you again, Erik.
Thanks a lot.